Hello everyone, I'm Sebastian Y and this is Managerial Economics. In this video we're going to talk about how to use polynomial functional forms in a regression. We'll frame all of our discussion about polynomials with an example. We're going to be looking at data from the 2014 American Community Survey. Using that data, we're going to be thinking about the relationship between age and wage. Let's start out with a basic linear model. It's going to look something like this. Wage equals beta naught plus beta 1 age plus epsilon. Wage is measured in dollars, age is measured in years. What this tells us is that every time age goes up by 1, wage is going to change by beta 1. Since this is a linear model, it does not matter what the age is, that relationship stays the same. Going from 20 to 21 gives the same change in wage as going from 50 to 51. In general, we probably would imagine this beta 1 is positive. People who are older tend to have higher wages. Because people who are older tend to have more experience and education, we tend to think that people who are older have higher wages. Note we are not making a causal claim here. We'll talk about that in the next set of videos. Just that higher ages tend to be accompanied by higher wages. However, we might think it's not too realistic that this relationship stays constant throughout a person's entire life. Eventually, people's careers start to peak out and their wages will stabilize or even start to go down as they start to work less as they get older. Over here in Excel, we have our age and wage data from the American Community Survey. First thing I'm going to do is run our baseline linear regression. For the Y range, I'm going to take our wage, and for the X range, we're going to use the age. Running this regression, what we see here is each year of age is expected to come with about $600 higher yearly wage. If we look at a graph of this, we can see that it's a gently upward sloping line, but we can also see from the data this might not hold true as people get older. The way we're going to deal with this issue is by using a quadratic model. A quadratic model adds a squared term onto our regression. So we have beta 2 age squared. This is going to allow us to have a regression parabola instead of a regression line. And this is going to add some nuance to our results. If we want to think about what happens when wage increases, over in the linear model, we can take the derivative of wage with respect to age, and what we get is beta 1. Down here in the quadratic model, if we take the derivative of wage with respect to age, what we get is beta 1 plus 2 beta 2 times age. In the linear model, the relationship between wage and age does not depend on the age. It's the same no matter how old you are. But in the quadratic model, the relationship does depend on age. Let's estimate a quadratic model in Excel. I'm going to add a new column here that I'm going to call age 2 for age squared, and I'm going to define that as age squared. I'll then copy that formula all the way down and then run the regression. My Y range is going to be the wage. X range is going to be age and age squared. You always want to include the linear term in the quadratic model. That is going to allow us to build the shape that we want to build here. Running this regression, what we see is a big positive number on the age coefficient and a smaller negative number on the age squared coefficient. Going back to our model, if beta 1 is a big positive number and beta 2 is a small negative number, this means the relationship between wage and age will start out as a positive when age is relatively small, but as age gets bigger, that negative part of this equation starts to get bigger and bigger and bigger, which slows down the wage growth until eventually it starts to pull it down. This represents careers reaching their peak. If we want to figure out the point where wages reach their peak, all we need to do is set our derivative equal to 0. That is, make the first order condition. This is something we've done before trying to find the top of a parabola. To find the age where wages peak, we just solve for age in this equation. So if I subtract beta 1 from both sides, I get beta 1 equals 2 beta 2 age. Then divide both sides by 2 beta 2 to get age equals negative beta 1 over 2 beta 2. Of course, age cannot be negative, but this is going to be a positive number because we have a negative number for beta 2. As before, we want to always use Excel for these type of calculations so that we can avoid rounding as much as possible. So I'm going to plug in my formula here, negative beta 1, so that's going to be this number right here, and then divide that by 2 times beta 2, which is this number right here. And what we get is about 50, meaning that on average, age 50 is about where we expect wages to peak. Looking at the graph, we can see a parabola with its top somewhere around age 50. The graph does reveal one small issue here, that at extremely high ages, we actually see our predicted wage, given by the red parabola, dropping into the negatives. Obviously, we can't have a negative income. Regressions often do have limitations in this way. It is worth pointing out, though, that people who are still in the labor force past the age of 85 are relatively rare, so this is not a huge problem. Polynomial regression models do not just have to stop at quadratic. We can keep adding more terms and get a cubic model. This is going to look something like wage equals beta naught plus beta 1 age plus beta 2 age squared plus beta 3 age cubed plus epsilon. Remember again to always include the lower order terms as we add more. This is what allows us to build a complex, nuanced shape in our curve. You can also keep going to a quadratic model and add an age to the fourth term, and even further if you want. Back over in Excel, I'm going to add an age cubed term to see what happens. I'm going to define that as age to the third, and then copy that formula down. Let's run the regression. We would then take these coefficient estimates that we get and plug those into our equation. Now the question is, was this worth doing? One way to answer that is to look at the r squared. Let's go back to our linear model. The r squared we have here is about 2.7%. When we went to the quadratic model, that jumped up to about 7.4%. That's a big increase. Going over to the cubic model, we actually gain very little in terms of r squared. So this addition could be useful, but it's not adding a lot. Now let's go back and add one more term. We're going to make an age to the fourth term. Copy that all the way down. Then we're going to run the regression. Looking at the r squared with this one, it's basically not changed from the cubic model. This suggests the age to the fourth term is probably unnecessary. Each time you add another higher order polynomial term to the regression, that is going to give you more opportunity for nuance in the curve that we are estimating. The decision of when to stop is entirely subjective, but keep in mind what you're gaining from that increased complexity. I put on the screen the predicted curves from all 4 of the models we estimated here. You can see the linear model stands out the most. Going to the quadratic model is a huge advantage here. The cubic model does add a bit of nuance and eliminates the problem of the negative incomes at the very high ages. So overall, I would say that's worth doing, but the quadratic model is almost identical to the cubic, so I wouldn't go that far. This brings us to the end of our second chunk of material on regression. If you have any questions, feel free to let me know. Thanks for watching.